comments time. Do you have any questions before we go? No. Okay, you're free to go. So how's the room? Is everything okay there? Yeah. What are you doing?
Okay, so where were we? Should probably share the screen. Okay, so we're going to be working in Mathematica. So if you haven't already, download the Mathematica file from Tuesday. And then we're going to go into ZMax. So the ZMax file from Tuesday. All right, how many people have we got? 13. Oh, wait another minute or two. Oops. Okay, how many have we got now? I'll wait one more minute. So you open up Mathematica, remember that if you don't hit Shift Enter on key lines like the definitions of the matrices, then it won't know what they are and it won't give you what you need. All right, let's get started. So at the end of the last class, we were constructing the matrix for a thick lens. And this is outlined in the file I posted. We have to first send a bunch of parallel rays from air to glass. And we're going to do that across a curved surface with radius R1. We're going from an index of 1 to an index of NG for the glass. Then we're going to go a distance T, the thickness of the glass. So that's our translation matrix. Then we're going to go across another curved surface. And you have to reverse the order of the indices because now we're going from glass to air instead of from air to glass. And then what was the purpose of that last translation? What is the thing that we're figuring out by translating one more step through a distance x?
Is that the distance from our lens to the image?
It is the distance from the lens to the image. And since these rays are coming in parallel to each other, what is the name of the plane that that image is in?
Focal plane.
That's right. It's the distance from the lens to the focal plane. And so we get that, and we get some complicated expression for X. And we'll play around with that in a little bit. Now, that matrix is the lower right, that element, excuse me, is the lower right element of the matrix. I'll show it more explicitly. It is, sorry. We had to solve for, we had to set this lower right element to 0. Because if we're in the focal plane, parallel rays are coming together no matter what Y value they started off at, whether they were hitting the lens down here or here or here or anywhere, at any Y value that they're coming in at, they all go to the same focal point in the focal plane in the end. So we had to set this equal to 0. Now, if we set this lower right element equal to 0, then Y2 should just be equal to the lower left element multiplied by theta 1. So what is the physical interpretation of this lower left element here?
Is it the focal length?
Yes, it is. And we got that the focal length was equal to this messy thing, which doesn't mean much, but 1 over the focal length was this. And when we started doing the algebra, I got confused and forgot one key fact, which a student reminded me of after class. And that key fact is this: we've got that 1 over F is equal to n minus 1 over R1 plus 1 minus n over R2, which would be the same as n minus 1 over negative R2, plus the thickness times n minus 1 squared, because we've got an n minus 1, well, you can't see the Mathematica file now, but it's the thickness times n minus 1 squared over n R1 R2. And here's the thing I was worried about. Not that anybody would ever make a lens that's way thicker than the focal length, but if we did, it's a case where we sort of know what the physics should be. We should be able to check it. If we did that, then the rays would come to a focus here, and then they would keep on going to the other side, and they would then come to a focus below the axis. All right. And so we had better have that the effective focal length is negative, because this distance here is Y2, and that's negative. And theta 1 is positive, and Y2 equals the focal length of this thick lens times theta 1. If this is plus and this is minus, then this has got to be minus. And what I was worried because I didn't see a minus sign in this last term. The thickness is a positive number, n minus 1 squared is a positive number, n is positive. Well, R1 is positive, but R2 is negative. And so if I make it thick enough, then we do indeed get a negative focal length. Any questions? Well, let's plug in some numbers here. All right, I'm going to go back to my other screen. I'll share that. And all right, if I go back to my other screen, then I want to take note of the values of X and F. All right, so the easiest way to do this is to just simply give it some numbers. And let me see what I put into my Zmax file. I'm going to make these 10 and I'm going to make this fixed right now, -10. And I selected the material N15, which is just a simple refractive index of 1.5. So I can say NG equals 1.5, R1 equals 10, and R2 equals -10. And I've also got to plug in a thickness. Let's make this nice and thick to make the effects that we're going to see rather dramatic. Okay, if we make it nice and thick, 2 centimeters, then let's just ask it what the focal length is, element 2,1. And yes, Mathematica requires that if you're accessing the elements of a matrix, it's matrix name double bracket and then the indices of whatever element, because functions have a single bracket, so elements of a matrix have double brackets. And it says that focal length is 10.3448. And lo and behold, Zmax says 10.3448. Any questions so far? Well, let's, the situation we have here, is this the situation that we actually calculated in Mathematica? What was the assumption I told you we were making when we set up those matrices for the thick lens? Were we sending in a bunch of rays that came from a single point on axis and went at different angles from that point? No. We were sending in rays parallel to the axis, which means they were coming from infinity. So let's just insert a surface after that so that we can make this infinity, and then our fields are no longer object height, they've got to be angle. Okay, well, sure enough, our image isn't in focus anymore, so we optimize it. All right, let's see here. It says that last layer thickness is 9.647, not the focal length of 10.3448. Let's see what X is. 9.65517, and it's slightly different. Now, why would our rays 9.647 instead of 655? Any idea why things are coming to a focus a little bit closer than what our matrix calculation predicted?
Do we have the 2 fields set up in Zmax, and so it's optimizing between the 2?
And the off-axis field is going to come to a focus a little bit further, and that's good. Still not quite. What else is going on that might explain why? I mean, it's a small difference, but it's a difference. And we got the focal length so exactly before. So it's a little bit frustrating. Why might we not be seeing exactly what we predicted with our matrix calculation? Something aberrant about this. Don't like my pun? Don't get my pun? Something aberrant. What would make those rays come to a focus a little bit closer than we would have predicted?
Professor,
Yeah.
take a shot at it, and I
Sure.
will guess your pun is relating to something about aberrations.
Yes, spherical aberration, which always causes rays to come, well, the further out rays to come to a focus a little bit closer in. So how can we reduce the effects of aberration?
Well, one way is to lower the aperture, right?
Yep, let's do that. Let's cut it in half, and then we'll refocus. And now it's 9.654, and our matrix calculation predicted 9.65517. And I'll bet that if we narrow it even more, then there you go. I'm sure that technically, if we went enough decimal places, it wouldn't be quite there. But you see, we get closer and closer. That's the thing I want you to remember, that this matrix theory is all based on paraxial approximations. And it becomes closer and closer to what's actually going on as you make your apertures smaller and smaller. All right, so it looks to me like we've more or less confirmed it. Now, why is it? Well, let's see here. Now let's talk about the principal point, because I've been saying that, let me switch to drawing by hand again. A basic model that turns out to work for paraxial optics is this. For a lens, you have two special planes called principal planes, right? And you have a focal point and a focal plane, and another focal plane on the left. And if I send in rays parallel to the axis, or parallel to each other at least, these are coming in slightly off axis, they're going to do all sorts of complicated things inside the lens, but they are going to come to a focus off axis and that focal plane that they come to a focus in is one focal length away from the principal plane. Now, if all we did with the principal plane, and there's a right principal plane, and there's a left principal plane. If all we did with the principal plane is simply say, hey, it's one focal length away from the focal plane, and we know how to find the focal plane. The focal plane is something that we can, assign an immediate physical meaning to. It's where parallel rays come to a focus. Well, that wouldn't be very interesting. But if I had set up a more interesting problem. If I again draw my principal planes and the exact calculation, there are formulas that you can look up. Before I had really gone into matrix optics, I would look up these formulas and plug in chug, and I would say, okay, the distance into the lens, this little distance here is equal to some mess involving R1, R2, and the thickness. If you really want to do it that way, you can. But what I always just do is I find the focal plane. By seeing how far away do the parallel rays come to a focus. 2, I find my focal length by seeing how far off axis do they come to a focus. And then 3, my principal plane is 1 focal length away. Here is the beauty of principal plane. If I've got an object right here, I can measure S1 from the principal plane, and I can measure S2 from the other principal plane, and I can then say that 1 over S1 plus 1 over S2 is 1 over F. This equation turns out to still be true, even if we have a thick lens. Even though it's called the thin lens equation, if you measure S1 and S2 correctly, if you measure them with respect to the principal planes, then the thin lens equation is indeed satisfied. Any questions so far? So let's go back into Zmax then. And what I'm going to do is I am going to, first of all, get rid of this. I'm going to make this layer have finite thickness and get rid of this second layer. And then in my layout, I'm going to have it display from surface 0. And then what I'm going to do is I'm going to tell Zmax that I want this last layer to have the same thickness as the first layer. Okay? That's all I'm going to do. Now, when we do that, and we'll make the aperture a little bit wider just so we can see what's going on. All right. Now, these two layers, the object and image distances from the lens, are the same. That doesn't yet mean that the image is in focus. All right, you have to zoom in quite a bit to see that it's not in focus. If I were to zoom out, it would be a little more apparent that they're not quite in focus. But what I'm going to do is I'm going to tell Zmax to do a quick adjust, right? And play with this first layer thickness. Now, why am I doing that? Okay. If the object and image distances are the same, then the object and image distances must both be 2f. And our focal length was 10.34. So our object and image distances must be 20.68. Now you could look in here and say, well, that's not 20.68. And I could make the thing smaller and the aperture smaller, and we could redo our quick adjust. And it increases it to 20. And I could verify that we're at the point of diminishing returns by changing it again and doing another quick adjust. And still 20. And now I'm going to make it 0.5 or 1 just so that we can actually see things in the diagram. But okay, the object and image distances from the lens surface are 20, even though I'm going around saying that they must really be 20.68 something, because they must be 2 times the focal length, and the focal length is 10.34 something. Where's that 20.68 measured from?
Is it from the center of the lens?
Oh, let's see here. It's from the center of the lens. Thickness of the lens is 2. So they're 21 from the center of the lens, not 20.68. That prediction that the object and image distances are 2f, that prediction comes from the thin lens equation, right? 1 over S1 plus 1 over S2 is 1 over f, and S1 and S2 are the same if they're both 2f. So if I'm saying that they've got to be, that those distances are 2f from something, what did I say just a few minutes ago about when we can still use the thin lens equation, where we have to measure things from if we work with the thin lens equation?
You have to measure from the left and right principal planes.
To measure from the principal plane. And the principal plane is not right at the lens surface. The principal plane must be 20.668 away. So it must be 0.668 inside, and that's so important that I'm just going to, I think I'll actually annotate it on here. I don't usually use Zmax's annotate tools, but I can. All right, so the principal point is 0.668 from the lens surface. Now, how we could find, we know it's 0.668 from the lens surface, and we know it's 10.348 from the focal point. How are we going to remind ourselves of where the focal point is, other than by, I don't know, going back and checking the video, which is not yet posted? How are we going to remember where the focal point is? We can either do something in Zmax, set up a situation in Zmax and see where something happens, or we can check in our matrix calculations. If we tried to set up a physical situation in Zmax, what would that be? How do we always find a focal plane?
The object at infinity.
Yep, let's put an object at infinity. So I better undo this pickup. Then we do a quick focus and we get that it's 9.63, except that's probably not quite right. 9.655. So 9.655 away from the lens. Okay, 9.655. So then the focal length must be the distance from the focal plane here to the principal plane must be 9.655 plus 0.668. And that is 10.323, which is very close. Wait, was it 0.668 or 0.688? Should have been 0.688. $10.343. And we've got that the focal length is 10.3448. Any questions? So what I want you to do here in this assignment is I am giving you a lens file. All right. And let's go look at that lens file on Blackboard. So if you go and look at project 6 principal points, you will see the PDF of the assignment and you will see a Cook triplet lens file. So go ahead and open those. Give you another minute to download. All right, anybody need more time to open the Cook triplet? All right, hearing no one. The Cook triplet is a famous camera lens. Modern camera lenses are a little more sophisticated, but still have a lot of the same ideas in many cases. There's 3 lenses, and the middle one has a negative focal length because it gets rid of field curvature. Because remember when I said during the class on aberrations that the field curvature, you can figure out the field curvature by saying that 1 over the field curvature is the sum of 1 over the refractive index of each lens multiplied by the focal length of each lens. And so if you have some positive lenses and a negative lens, as long as you pick the right value for that negative focal length, then you will cancel out the field curvature. And so what I want you to do is first, in this assignment, figure out, well, let me get the file onto that screen, okay. Is to first figure out the focal length and the focal length and the position of the principal planes. And again, the focal length, the position of the focal plane, you already basically know. It's right here. That must be the position of the focal plane. Actually, not quite, because I put this at finite conjugate, but you could just make this layer thickness infinity. And then you would figure out, and then you would be able to determine where the focal plane is. But it would be pretty close to there because this object distance is pretty large. How would you find the focal length?
Couldn't we set the object at infinity and then do a quick focus?
Okay, so we can certainly do that. I'm going to put in another layer. So first I'll make this one infinity, and I'll make this one like 10. Let's check our fields. Okay. And then we can do a quick focus. That just gives us the position of the focal plane. How do we find the focal length?
By using y equals f tan theta.
Yep, I should put one of my fields off axis, say, I don't know, 3 degrees. And then I would say, okay, this, whatever this height is, looks like 2.5. I don't know, I'd probably look at a spot diagram. It says it's 2.618 off axis. 2.618y must be equal to f times tan of 3 degrees. Boom. And whatever that number might be, then you're going to say, okay, well, the principal plane on the right must be that distance away from the image plane. Any questions so far?
I missed that explanation with the spot diagram. Can you go over that again, please?
Oh, on the spot diagram, the nice thing about the spot diagram is it tells you exactly how far off axis the center of that image is. And it's saying that the center of this image is 2.618, I assume millimeters, although sometimes it's been known to screw up the, no, 2.618 millimeters off axis, right? So that 2.618 millimeter distance, or this distance here, must be equal to the focal length multiplied by the tangent of 3 degrees.
Okay, I got it. Thank you.
You're welcome. All right, now how am I going to find, so the principal plane must be, well, let's just do this in Mathematica right now. Focal length would be 2.618 divided by the tangent of 3 times pi over 180. 49.95. So it's 49.95 to the left. That last layer thickness is 42, so 42 point something. So it's got to be about 7 millimeters in. How are we going to find the left principal plane? Well, the principal plane is one focal length away from the principal point. Sorry, from the focal point. The principal plane is one focal length away from the focal point. So we know what the focal length is. It's 49 point something. How are we going to find the left focal point? Can't delete the object surface. What would happen if I put something at the focal point?
The image forms at infinity.
What?
The image will form very far away, so length will be like what's it called?
Yep.
Parallel.
We're going to get a bunch of parallel rays.
Yeah.
I don't know if this is exactly focused, but it's pretty good. I honestly just guessed that one. I did not have it memorized that it's 40. But clearly, I got pretty close. So I would say, okay, the focal point on the left is around here. And then the principal plane must be 49 to the right of that. It's that first lens thickness is 3, and then it's 6. Oh, it must be around here. Any questions on that idea?
Could you go over that one more time, Professor? Sorry.
So, okay, so the focal plane is one focal length away from the principal plane. So if our focal plane is right here and our focal length is like 49, then our principal plane must be 49 millimeters to the right of this point, which would be, see, 40 plus 3 plus 6. So probably not exactly at this surface, but very close to it.
Oh, okay, thank you.
I have a question. Is there a better way to place or like change the object thickness besides just guessing and seeing how the rays turn out?
Sure, one thing we could do is we could work with an afocal image space. And then we could ask, where do we have to place it so that the rays aren't spread out? If we work with an afocal image space, then then we could put our image plane at infinity. So we'll have an image plane and insert a surface after. And for some reason, when you put the image at infinity, Zmax tries to draw infinity, but when you put the object at infinity, it knows better. Okay, so we've got our image at infinity. We're seeing how the rays are spread out. What is the angular spread of the rays? So I move left and right, up and down. Now the units are not millimeters, the units are milliradians. So now I could decide to play with this thickness and do a quick adjust on it. And we get 37.376, and those rays still look pretty parallel. And here's our angular distribution of rays. And you might ask, well, what happens if we narrow the aperture? Okay, so now we'll do a quick adjust on that. Oh, I was not expecting that. What happened? What? I have no idea what just happened there. The last time Zmax spaced out on me like that, I gave a wavelength 0 weight, but everything here that is bizarre. If I go back up to 4, now it works. I go down to 2. It works. I go down to 1.3. But let's pretend that didn't happen. It was working for a while, and I just changed one thing that I wasn't paying attention to, and you probably won't change that one thing. So I made a very rare error. You probably won't make my error. And there is a very simple way to undo my error, which is to quit without saving, close the program, and then reopen it. Now there's a time to save your work, and that's when things are going well. And there's a time to delete your work, and that's when things are not going well. When things are not going well, you turn off the program, close the program, and restart it. Anyway, while I wait for all this to load, any questions on the concept of this assignment? Okay. So let's go back and try that again. We insert a surface after. We make this infinity. Go to our layout, because for some reason Zmax tries to draw infinity on the right. We take it to surface 7. Okay. Then we go to an afocal image space. Okay. Then we adjust the surface thickness to optimize our spot diagram in our afocal image space. And our spot diagram not what I was expecting at all. I checked afocal image space. It looks nice and focused. And now it's working. And because it's working, I save. And then I start changing things. And then I do a quick adjust. I go to my spot diagram. And suddenly it is declaring that things have size 0. Maybe I can force things to scale. And things are behaving weird. So when things behave weird, we just quit the program and then we try it over again, having already saved it with settings that worked. I know it's a very old and timeless lesson, but it's a lesson that even I need to constantly relearn at times. Anyway, questions? Here's the point. The point is that we've got a pretty good estimate right now of where the focal plane is. And we know that the principal plane is one focal length to the right of that. And so we know where the we know where the principal plane is 49 is one focal length to the right of that, and we know that the focal length is about 49. And so we work with that. You're going to do the same thing for a pair of plano-convex lenses. And then you're going to test the thin lens equation by just setting an object somewhere, seeing where the image forms, setting an object somewhere and seeing where the image forms. Now you're going to have a bunch of layer thicknesses each time. And remember, those layer thicknesses are not S1 and S2. You're going to have to add something to those layer thicknesses in order to get S1 and S2. But if you've got S1 and S2 correctly, then you should be able to make graphs of 1 over S2 versus 1 over S1. Any questions? How about we take the next 10 minutes as ZMAX work time, so that while you've got these ideas fresh in your mind, you can start working on things, maybe set up your spreadsheet, set up your file or your ZMAX file, write some notes to self, and I'll just take questions. And otherwise I'll be sitting here reading while I wait for you to ask a question.
I have kind of an unrelated question.
Okay.
I was just reading your assignment about the Cook lens. It was first patented in 1893. How does patenting process of a lens system go? I didn't really think about that. So, like, does Cook get a bunch of money for whoever uses this lens system?
Well, Cook only got money. I'm not sure what the duration of a patent was in 1893, but in the modern era, it's something like at most 20 years.
Okay.
So he wouldn't be getting that now. So the way a patent works in general is that if someone makes and sells a product that uses your intellectual property, then you can get some kind of royalty from it. You know exactly how much of a royalty. I mean, it's your intellectual property. They can only make things with that with your permission. So you can demand a royalty. Now, then the big question is, well, how similar is similar enough? And to answer that question, ask a patent lawyer. And the value of patents really depends on the type of product and whether the precedents make it easy or difficult to enforce a patent on that type of device or that type of process. Sometimes it works better than others. But for the duration of the patent, you can either tell people, nope, you can't make this at all, or you can make it, but you got to pay me a royalty.
Okay. Yeah, I just never thought about patents for lens systems before. Like we're doing all these systems in ZMAX and I thought it was cool.
Yeah, so the patent would probably say, well, we have lenses of these shapes with these relative focal lengths set up in this manner to achieve this effect. And then one question is, well, what if someone improved on it? Would that improvement be its own patentable thing, or would it be too derivative and they have to owe? And you got to ask a patent lawyer about that. Oftentimes enforcing a patent is difficult, but the reason why patents exist is, on the one hand, to give people at least sometimes an opportunity to defend their intellectual property so that they can reap a big reward. That's supposed to be the incentive for innovation. But on the other hand, they also have to disclose things. Patents are public. So if you patent something, then yeah, no one else can make that for 18 or 20 years or whatever the current term is. But on the other hand, you have to tell everyone what you did, which means that now everyone else can try to improve on it. So it's a balancing of interests. You get the benefit of your invention, everybody else gets the benefit of knowledge for further innovation. Does it work as promised? Not necessarily. Patent experts could tell you all the upsides and downsides of it, but that's the basic idea.
Awesome. Thank you.
Mm-hmm. Other questions? On, I don't know, maybe the assignment instead of patent law. So apparently the pharmaceutical companies that made the vaccines are, for very understandable PR reasons, being pretty lenient about enforcing their intellectual property rights. Because frankly, the big bonanza for them is not just going to be the money from this. I mean, yes, they are getting money for these vaccines. But if someone else gets to make that vaccine too, I mean, as far as PR, hey, they look pretty good. They let someone else do it too so that they can save the world. But the real bonanza for them, besides the fact that their name, I mean, I got the Pfizer vaccine. I didn't get I'm looking at my card. It doesn't say, I don't know, the name of whatever RNA technology is in there. It says the Pfizer vaccine. So for a generation, you know, people, imagine if instead of saying penicillin, they said the name of the drug company. You know, the first mass market antibiotic was not named penicillin, but was named after a company. I have no idea what the name of that vaccine is, like the product name or scientific name. I just know it's the Pfizer vaccine. they're banking on that goodwill. The other thing they're apparently banking on is that a lot of this technology is fairly new. It's getting its first worldwide trial right now, and so far it's saving the world. And so they're betting that a successful outcome from this means that they will be able to develop other types of vaccines using these RNA technologies that will provide a big boon, both as a test of, as a proof of concept, and also general goodwill and marketing, and of course a short-term infusion of cash to fund all of the R&D. But apparently they're already moving very rapidly on other types of vaccines that use these technologies. And so that's going to be the big bonanza for them. So I think, frankly, you know, they would probably be pretty generous to anyone who says, hey, can we also manufacture this in order to save a bunch of lives? They'll be like, sure. You can tell everyone that you are making the Pfizer vaccine or the Moderna vaccine or the whatever vaccine, as long as you tell them that it's our name on the thing that saved their lives and our generosity, because they're doing free advertising right now, and they're making they're experimenting with mRNA vaccines for a whole bunch of other diseases. Anyway, with that, I'm going to take a 10-minute break, and at 6:10, we will come back and do some more matrices. I want to show you some other applications of matrix optics.
Dr. Small, a question. The Galileo's dialogue, is it, you mean controversial at the time or still controversial?
Oh, Professor, you're
Nowadays,
muted.
it's not yes, I was muted. Nowadays, it's not controversial, but he did get placed under arrest for it, and it was placed on the index of banned books. So, yeah, it was pretty controversial once upon a time. Any book that you can get in legal trouble for is usually controversial with someone. But it's also a book that frankly presaged Einstein, his thought experiment about the boat and how you cannot observe whether or not you're in a moving reference frame as long as you make local measurements, was really very, very close to all the ideas of the theory of relativity. If he had known that the speed of light was the same to all observers, he probably would have derived relativity. Anyway. All right. We'll deal with Galileo next fall. Let's do matrices for a few more lens systems as practice for what we've already done and warm up for next week when we're going to talk about zoom lenses. So let's talk about this lens system. Right? We'll say this has focal length minus f, and this is plus f. So these two lenses have equal and opposite focal lengths. And if we wanted to figure out, well, we already figured out a few weeks ago what the focal length is. And we said that the effective focal length of this is given by, she's given by this formula. This is how it's usually written. 1 over f1 plus 1 over f2 minus d over f1, f2. Call this separation d. So 1 over the effective focal length would be 1 over, in this case, minus f, plus 1 over f, minus d over minus f squared. Those two cancel. This minus cancels that minus. And 1 over f is that. So f effective is f squared over d. Now, in general, in order to figure out where the focal points are, we need to do some sort of elaborate matrix calculation. But this one doesn't require an elaborate matrix calculation. We can figure this one out by hand, and it helps illustrate the concept. So what kind of experiment would we set up to find the right focal point? Anyone?
To find the effective focal length of the system?
Not the focal length, to find the right focal point. The point where parallel rays get focused to. What kind of experiment? Come on, guys. We just send in rays of
Having the
light.
object in infinity.
Yeah. We just start with an object at infinity. Now, a lens like this, what happens to the rays when they hit this first lens?
They diverge rather than converge.
And where do they diverge from?
as if they were coming from the focal point on the left.
Yep, so they diverge as though they're coming from over here. Oops, that was not what I wanted. Wrong thing there. So they act as though they're coming from there. All right, so then this is F plus D. And so we're going to have, we can figure out where they come to a focus over here. 1 over F plus D plus 1 over S2 equals, now are we using what? It's going to be 1 over a focal length. Is it 1 over the effective focal length, or is it 1 over the focal length of the right lens?
1 over the focal length of the right lens.
Yep, because the right lens has no idea that it's part of a bigger system. It just knows that it's getting a bunch of rays that act like they're coming from over there. So 1 over S2 equals 1 over F minus 1 over F plus D. And then S2 is equal to 1 over all of that. So S2 is F squared over D plus F. Okay. Where is the principal plane? Wait, I feel like, no, S1F over S1 minus F. Yeah. Yeah. Okay. So where is the principal plane? How, I mean, think about the ZMAX assignment you were allegedly just working on 15 minutes ago. Where, once you know the position of the focal plane, how do you figure out where the principal plane is for, say, that Cook triplet?
It's just the focal plane minus, it's like it's one focal length away from the focal plane is the right focal.
Now, what focal length are we using? Are we using the focal length of this single lens here, or are we using the focal length of the entire system?
The entire system.
Yeah, the principal plane of the system is one focal length of the system away from the focal point of the system. So this is going to be F squared over D. All right, and so if this, I'll redraw it down here because it's gotten kind of messy. All right, and so we've got a bunch of rays coming to a focus here. This distance was F plus F squared over D. And then this distance is just F squared over D. So this distance is F. So in this very special case, the principal plane of the system is the focal plane of a single lens. That is not usually the case, but in this one special case, it is. Any questions so far?
What do you mean of a single lens?
I mean that this lens right here, just taken on its own, has focal points. And it just so happens that the principal plane of the bigger system matches up with the focal plane of one of the constituent lenses. And the reason is because this system has a special symmetry to it, that we've got plus F here and minus F there. So it's a very special case. I chose it because it's an easy case to work with by hand. And so we could think conceptually about, well, where do things happen, and then deduce where the focal points are, where the principal planes are, and so forth. Other questions? Okay, let's figure out where the left focal plane is.
Actually, Professor, sorry. How do we know that f squared over d is that little distance there?
Because f squared over d is the focal length of the system.
Oh, it's a effective focal length, right?
Yeah.
Thank you.
Other questions?
Professor, so if I were to if I wanted to find the principal plane on the other side, I guess figuratively I would mirror the same like approach, but the other way. Okay.
Yeah, this is what we're going to do. So again, since that diagram is busy, I will just replicate it one more time. So what we do is we send a bunch of rays parallel to the axis, and they are going to come to a focus. I'm gonna maybe, I assume none of this is to scale. Let's consider the possibility that it's like that. All right, so this is D. And yeah, I know that doesn't make a whole lot of sense. Yeah, no, that'll work. All right, and so this must be F minus D, 1 over S1 plus 1 over S2 equals 1 over negative F. Except now S1 is negative. So while this distance here to where the image would form is F minus D, this is a virtual object. And virtual objects form at a negative distance. So that's 1 over D minus F. And you might be saying, well, what if it had been the other way? What if I had drawn it like that and the focal point was there? Well, then guess what? This would be F. This would be D minus F. I know that's, all right. So it works either way. If the image forms right here, then we've got a positive distance D minus F for S1. If the image forms there, we've got a negative distance D minus F for S1. Questions on what I did there? right, so 1 over S2 is 1 over negative F minus 1 over D minus F. S2 is 1 over, I'm gonna write that as negative 1 over F plus 1 over D minus F, because there's a minus here and a minus there. So that's F times D minus F over any questions? Anyone? Let's check that. Let's check that in Mathematica. So I'm just going to scroll down to the bottom here and create a new section. Two lens combo, I'll label it as a section. Okay, so now M is going to be, well, let's see here. I've got to send light through, I've got to translate it through some unknown. First, I've got to send it through the first lens. So we're going to do lens of minus F. Then we're going to send it a distance D. And then finally, we are going to send it some unknown distance. Well, I already used X, so I'll call it Z. All right, if I want to figure out how far to the right we have to send everything so that the rays come together, then I'm basically solving for Z. If we're in the focal plane on the right, which of these matrix elements will be 0? We're sending in rays from infinity.
We're sending in rays from infinity from which side again?
From the left. So we've got a bunch of rays coming from infinity on the left. And so first they go through the negative lens. Then they go between the lenses, a distance D. Then they go through the positive lens. Then they go an additional distance Z. And they all meet at some point off axis, given by y equals f tan theta. So if y equals f tan theta, which matrix element is 0?
The bottom right one?
The bottom right one, yeah, because if we multiplied it by a vector, go back to the writing by hand for a moment. If we've got this matrix, if we've just got a couple of lenses sending in parallel rays, they're all coming to a focus right there. Which is roughly f theta. theta 2 y2 equals a, b, c, d acting on theta 1 y1. y2 equals c theta 1 plus d y1. And in this case, y2 doesn't depend on y1. So d must be 0. So then in Mathematica, it's got to be the bottom right element that is 0. So I'm going to set that bottom right element to 0. I'm going to solve for z. That's just a way of telling it. And lo and behold, it gets that it's fd plus f squared all over d. That's exactly what we got before. All right, so let's say that z equals f times d plus f over d. And then which element would be the focal length? When we get y2 is going to be equal to one matrix element times theta plus another matrix element times y. Which matrix element multiplies theta?
The top right one.
The top right one multiplies theta. The left column is always multiplying y, because remember, theta's on top of the vector. Let's see. I wish there was a way. I don't know how to get it to add in. I don't know a nice way to get Mathematica to display this, but theta is the top element of the vector. So actually write down the 2 by 2 matrix multiplying a 2-component column vector right now. I just want you to write down an ABCD 2 by 2 matrix multiplying a column vector with theta on top and y on the bottom. And then get your equation. Theta 2 equals something times theta 1 plus something times y1. y2 equals something times theta 1 plus something times y1.
It's the bottom left one.
Bottom left, yes, the bottom left is the thing that multiplies theta. So m of 2, 1. Oh, that's messy. I'm going to tell it, simplify it. F squared over d. Any questions on how I got that? Let's do another case. It's going to be relevant to zoom lenses next week. Let's do a telescope. Remember that the basic idea of a telescope is that you've got a lens with a long focal length and a lens with a short focal length. And they're separated by a distance f1 plus f2. And the whole idea is that all of these rays come to a focus at the first focal point. And then, or in the first focal plane, they're actually a little bit up there. You know what, let's do this right. I've got drawing tools, I can do this right. They come to a focus in the first focal plane I did not think that through when I did it. Okay, there. So they come to a focus right there. This is y equals f1 theta 1. And then they come out at an angle theta 2, given by y equals f2 theta 2. So theta 2 is f1 over f2 times theta 1. That was the whole idea of a telescope. And on a previous ZMAX assignment, you set up a system like that, and you indeed verified that theta 2 was related to theta 1 by the ratio of the focal lengths approximately. Now let's set that up with matrices, because we're going to be setting up some 3 and 4 lens systems next week, and we're going to prove that getting this kind of performance is in general tricky when we set up more complicated lens systems. So we would have to have theta 2 y2 equals acting on theta 1 y1. What's the first thing that would hit this column vector?
Would it be the left lens?
It would be the left lens. It's going to be 1 minus 1 over f1 0 1. Then what's going to hit it?
A translation of f1 plus f2.
And then finally,
and then the right lens.
then the right lens, 1 minus 1 over f2 0 1. Now, before we do the multiplication, let's just look at what theta 2 equals here. Theta 2 is equal to a constant times theta 1. If I wanted to, I could write that as plus 0 times y1. And I would put the 0 in there just because that's a way of reminding us that technically y1 was multiplied by a matrix element. Has to be. You can't just say, oh, I'm only going to multiply some of these matrix elements. I don't feel like doing all of them. But if that variable nonetheless didn't show up in the answer, even though you did the multiplication, it must be that the matrix element was 0. It's the only way well, that's one of the 2 ways. The other way is you could get a variable showing up in a few places and they all cancel out. But in general, the way that a variable doesn't show up in there is if you've got a 0 matrix element. So I am predicting that our matrix is going to be, well, I don't know exactly what the bottom row will be, but the top row, and oh, there's probably a minus sign there. It's going to probably be minus f1 over f2, 0, and then whatever. That's my prediction. Any questions on that prediction? This is a simple enough matrix problem that we could do it by hand. So that's our prediction. We'll do the actual multiplication in a different color. We'll do the matrix multiplication from left to right. It's associative, so that doesn't matter. If I do this multiplication, I get 1 times 1 minus 1 over f2 times all of that, minus f1 over f2, minus f2 over f2. And then I do 1 times 0 is 0, minus 1 over f2. Let's see here. Then I've got 0 times 1 and 1 times that. So I've got f1 plus f2. Then I've got 0 times 0 and 1 times that, which is just 1. Okay. See anything that I could simplify in what I currently have before we go on?
The f2 over f2 is just 1. And it
Yep.
cancels out. Well, it's a -1, but the -1 cancels out with the 1.
So I can rewrite this as minus f1 over f2, minus 1 over f2, f1 plus f2, 1, multiplying 1, minus 1 over f1, 0, 1, theta 1, y1. And now I'm worried, because when I do row dot column, no, we're going to be fine. So this row dotted with this column, I get minus f1 over f2 times 1 plus this times 0. Well, that's nothing. And then I get minus f1 over f2 times negative 1 over f1. Row dot column minus 1 over f2, which looks really worrisome. Except, let's see here, minus times minus is plus, f1 over f1 cancels. And yeah. So that was 1 over, that was just my bad handwriting. So I'm left with 1 over f2 minus 1 over f2. That's 0. And then, well, honestly, who cares about the rest of it? Because we were only trying to solve for theta, not for y, but we'll do it for completeness. Row dot column, and we're left with f1 plus f2 over minus f1 plus 1. And when all the dust settles, we are left with minus f1 over f2, 0, f1 plus f2, and minus f2 over f1. Any questions on the process? The physical interpretation is that this is our angular magnification. Also, this is an afocal system. What I mean by afocal is that if I try to send light into it, the light will never come to a focus, right? We'll never be able to bring all the rays to a point. We could verify that by sending the light, by adding in one more matrix. we could do a translation through a distance s multiplied by minus f1 over f2, 0 f1 plus f2 minus f2 over f1. And we could ask, when we do that, can we bring rays to a focus? Can we get the rays to a point where everything that started off at the same angle goes to the same y value? So we've got 1, 0, S1. And I'm just double checking. Yeah. We do that. Row dot column. We're just going to have minus f1 over f2. Row dot column, 1 times 0, 0 times that. That's nice and easy. S times minus f1 over f2 plus f1 plus f2 S times 0 minus 1 times f2 over f1. And so when all the dust settles, that's minus f1 over f2, 0 minus f1s over f2 plus f1 plus f2. And then we're just left with minus f2 over f1. Now, in order to bring things to a focus, in order to send a bunch of light in here on the left and get all the rays to come together on the right, which matrix element would have to be 0? That's what every matrix optics question comes down to. Theta 2, y2. Which matrix element would have to be 0 so that y2 is independent of y1?
Bottom right one.
Okay. Well, I can't think of any value of s that will make the, I can't think of any value of s that will make the bottom right matrix element 0. Just that question, are there other operations on a final matrix? I feel like someone must have come up with a situation where the determinant means something, but for all of the imaging situations that I've come across, I've never had to worry about it. So I won't say that the determinant or the trace or some other property of the matrix wouldn't be physically interesting because someone will find a case where it is. But I will say that to my knowledge, in all the cases and all the problems I've ever tried to solve, I haven't had to deal with it. Other questions? All right, if you remember nothing else from today, remember 2 things. First of all, that the principal plane is always 1 focal length away from the focal plane and vice versa. Remember that you find the focal plane by asking, where do parallel rays come together? And if parallel rays come together, that means that all the rays that started off with the same theta wind up at the same y, which means that the final y, that y2 is independent of y1 and a matrix element is 0. Next Monday, we're going to start talking about zoom lenses. Then we're going to probably have an alumni visitor. Sorry, not Monday, Tuesday. Next Tuesday, we're going to start off talking about zoom lenses. Then we'll probably have an alumni visitor. And then on Thursday, we'll continue with zoom lenses. Have a good weekend.